Hi, good evening, everyone. Can someone respond if my screen and audio is working? Can you see my screen? Okay, thank you. So let's wait for 2 or 3 minutes so other participants can also join and then we can start. Thank you, everyone, for joining the webinar. Okay, so let us start. Good evening, everyone, and thank you for being here. Today, we are going to explore one of the most powerful and exciting areas in AI, graph neural networks or GNNs. So over the next 1 hour, I want to speak about GNNs and I want to take you on a journey that moves from the basics of GNNs and we will cover the real world applications, how big companies like Google, LinkedIn, Twitter, Amazon use GNNs for their applications, how they are used in life sciences for drug discovery and protein folding. So I hope this will be an interesting session and we can make it interactive. We can have a Q&A session at the end of the webinar. So I think there are more participants in the waiting room. Okay, so let us get started. Graphs are not something that we see in our mathematics textbooks. Graphs are a natural way to see the world. They are unstructured data. So we have graphs everywhere around us. In social networks, where people are the vertices and edges of people and the relationships are the vertices and edges of a graph. We have molecules where atoms are connected. We have proteins that fold into complex shapes. Users interacting with online content, users engaging with products in e-commerce platforms. We have financial networks where the transactions, accounts, and the all these transactions are kind of relationship between the customers or the users in the financial network. So traditional deep learning models like CNNs and RNNs are designed for images and sequences. They struggle when the data is irregular, messy, and interconnected. And that is where graph neural networks comes in. In this session, let us understand what graph neural networks or GNNs are, why they are becoming essential in AI, why industries are rapidly adopting them, and how they are even enabling Nobel Prize winning innovations. My goal is that by the end of this webinar, you should be able to see graphs everywhere around you, understand how GNNs operate, and feel confident about how to start using GNNs in your own research domain, whether that is your research or your industry projects or your own interested research projects. So before we start the topic, let me introduce myself briefly. My name is Aishwarya Konavur. I come from a background in data science. I completed my master's in data science in 2020. I have had the privilege of working both in research and in industry. I have worked as an AI researcher at a multi-million dollar startup. I have also done academic research at University of Wyoming in USA. And in 2022, I founded Togo AI Labs with a vision of collaborating with people with a vision of helping people transition to AI, conduct research, publish the works, and be in the forefront of AI and GNN innovations. So my goal is to make advanced AI research like graph neural network research, temporal network, make everything accessible to students, researchers, and working professionals in India and across the world. At Togo AI Labs, we guide people through research collaborations. We also provide mentorship, and we also have few AI transition programs. My work in graph neural networks, especially temporal graph networks, received a Best Research Paper Award in 2023. So, one of the most proudest moments of my journey was being among the finalists in a national level program, TOEICathon 2021, where I had the opportunity to interact with PM Modi and present our work, which was an AI tool that translates Sanskrit into English. And I share this to say that I have walked the same path of many of you who might be on right now. I started with curiosity. I also struggled when I was reading complex papers. And I want to, in Togo AI Labs, I want to help everyone who struggle with research, conducting research, who has the curiosity to do something but need guidance or mentorship in completing the research projects, publishing the work. So my focus is mainly in graph neural networks. And currently, I'm collaborating with passionate students and researchers in different GNN and AI research projects. So this is a snapshot from the event Toycathon 2021. I led a team of 5 in Toycathon. It was organized by AICTE and Government of India along with collective ministries. The theme of the program was Heritage of India. So whatever we pitch in the event should align with the theme. We presented Samskriti, an AI solution that translated in Sanskrit verses or shlokas into English. It was using natural language processing. We used speech to text modules and we used NLP techniques to translate Sanskrit to generate English meaning. And this project was recognized at a national level by AICTE and Government of India. And that was when I got the opportunity to interact with PM Modi. It was a very interesting and exciting experience. And I will say this was the event that uh, it was the event in which I discovered my interest in conducting research, solving problems, and helping people to conduct research. And this was the main point when I decided to start building Togo AI labs. So I think we have more people in the waiting room. Let me admit them. I have continued my research journey collaborating with universities abroad. In 2023, I founded Togo AI Labs formally. And I would like to compare my story with the crow in the old story. The crow gathered pebbles to drink water from the pot. So my set of pebbles were the mathematics to understand research papers, AI research papers, and conduct the research. So it was a time when the GNN resources was very less available. I was not able to find enough resources anywhere on the internet. So I started reading the research papers. I started understanding them one by one. It was very difficult, and once I started understanding the mathematics behind GNNs and the AI models, it started becoming easy and clear. So I have been researching graph neural networks for the last 4.5 years, and now I have worked on different GNN research projects with different passionate people around the world. And these milestones represent a journey from curiosity to research. And now I'm building Togo AI Labs with the same vision in my mind. I want to help everyone who wish to transition into this field, which is still evolving, which is still new compared to other traditional machine learning or AI areas. And in this webinar, we will see where GNNs are used, how GNNs work, and different applications of graph neural network. And at Togo AI Labs, we have programs for people who wish to master graph neural networks, who wish to transition to AI, who wish to collaborate with us on conducting AI or graph neural network research. So this is the goal or agenda of today's webinar. We will start by understanding what graphs are, why they are everywhere around us, where are graphs used, why we need graph neural networks. We will understand about Google Knowledge Graphs, LinkedIn's Linksage, how Twitter's temporal graph network works, and how Twitter is using GNNs. We will see how molecules are modeled as graphs. And we will also have a question and answer session at the end of the webinar, so we can make it an interactive one. So let us get started. When we hear the word graph, we may think of the diagrams with circles and lines, right? In reality, graphs are the most natural ways to describe how world is connected. We have social networks like Instagram, Facebook, LinkedIn, where we have different people and the friendship connections. Every person can be an entity in the graph, and every friendship or follow or a like or a message can be an event. We call these entities as nodes or vertices of the graphs, and we call these relationships or events as the edge. So here, every person is a node, and every friendship or follow or the events like that can be an edge. There are social network platforms. There are e-commerce platforms like Amazon's, where users are connected to products, and there can be different types of events like viewing a product, purchasing a product, reviewing it, etc. So the products are connected to brands, categories, and sellers, right? This naturally forms a graph. In biology and chemistry, molecules are graphs of atoms and bonds. Proteins are graphs of amino acids. We also have navigation systems like Google Maps. It is a connection of road networks, right? So this Google Maps or a navigation map can be considered as a graph of locations. These locations can be the nodes or intersections, and roads can be the edges with distances and traffic. Where are other areas where we can find graphs? Finance and banking. In finance and banking, customers, bank accounts, transactions, they all form graphs. And how we can use graph neural networks? We can detect for fraud transactions. This fraud detection is about spotting unusual connections that happen in a graph. In recommendation systems, you will see people you may know or frequently brought together items. When we purchase something, we will get a notification like customers who brought this item also brought. So all these are graph problems. Once we train our mind to see data as not tables or images, we can see the world as a network of relationships and understand why we can model the real world data as graphs and use graph neural networks. Now, at this point, a natural question comes up. If we already have deep learning models like convolutional neural networks, RNNs, or LLMs, why do we need graph neural networks? The answer lies in the structure of the data. In an image, every pixel lies on a 2D grid. It has fixed neighbors. The pixel above, the pixel below. So here on the screen, you can see an image of a bird. If we are considering this as a collection of pixels, there will be fixed number of pixels and fixed number of neighbors. There will be a pixel above, a pixel below, right, on the diagonals, etc. So no matter what image you take, its neighborhood always stays fixed. And because of this consistency, convolutional neural network can slide filters across the image and capture patterns like the edges or textures and gradually learn the shapes, objects, and patterns. Each convolution layer gathers a larger receptive field here, and we have different layers like pooling layer uh, that downsample the information. And finally, we can say, okay, this bird, by understanding the patterns and features, by using a traditional convolutional neural network, we can say this image is of a bird, or if we have the image of a dog, then we can classify that as an image of a dog. Here, the data is highly structured and it is fixed. So the image can be perfectly structured like a grid. It follows Euclidean geometry. It has fixed number of neighbors. Similarly, if we have a text, these texts are sequences of words. So CNNs and RNNs can work here on this structured data because these are highly structured and that follow Euclidean geometry. Now, if we have a graph like a social network or molecules or proteins or a road network, these are real world data and these are not structured. It is not like a grid or it is not sequential. In a social network, one person can have 5 friends and another can have 5,000. A molecule of water can have 3 atoms, whereas another molecule, like a caffeine molecule, it can have different number of atoms. Just a second. So, if we have a road network in a small town, that network can be very simple. But in a large city, it is extremely tangled, right? So, there is no fixed shape, size, or ordering. And these kind of data, which are not structured like a grid and which is not structured, we call this data as non-Euclidean data. So, how we can use traditional neural networks like convolutional neural network on these unstructured data and learn the patterns? So traditional deep learning cannot handle this kind of irregularity. If we convert a graph into a matrix, like an adjacency matrix, then we can say, okay, these two nodes in the graph are connected. We can understand the relationships and meanings. So how we can, if we cannot slide filters on these unstructured data and learn the patterns, how we can learn the patterns from this unstructured data by using deep learning methods? This is exactly where graph neural networks or GNNs come in. So GNNs are designed to force graphs uh, into something where we can use deep learning to understand the patterns. Now we understood what graphs are and how we cannot use traditional deep learning models like convolutional neural networks on a graph. So the question is, what are GNNs and how they work? A GNN is a neural network that learns from relationships and connections between the data points. Think of every node in a graph as a person. Initially, each person knows very little about themselves and their own features, and they don't know anything about their neighbors. But as they start interacting with their neighbors, they learn from the features of their neighbors. These features can be anything like the experiences or the shared hobbies or anything. So when the people in a social network communicate, they exchange information with their neighbors and they learn. This is exactly what a GNN does. If we model a social network as a graph, and if we use a graph neural network to capture the patterns in that graph, each node updates the features by collecting information from its neighbor layer by layer. And this process is called as message passing. At the end of a few iterations, every node will have an embedding, and this embedding is just a mathematical vector that captures both the node's information and information that the node gathered from its neighbors. This embedding can be used to make predictions. So, what can be the predictions? It can be like what type of node is this, whether two nodes in a graph should be connected or not, what is the property of the entire graph. There can be different predictions like this, and we can use a graph neural network on a graph to understand these patterns and make predictions. So, how we can define a graph? Now, in that example, I said in a social network, people can be considered as the nodes of a graph. So, a graph is a collection of vertices, and we call these vertices as nodes, and these nodes can be considered as the information centers in the graph, and these nodes are connected with edges. Edges carry the information from one node to its neighboring nodes. The nodes can be entities like people, items, atoms, etc., and edges can be the relationship between the nodes. What can be the relationship? If that is a social network, the relationship can be friendships, bonds, transactions, etc. So GNNs work by processing the nodes, passing messages from nodes to its neighbors, and aggregating and updating the features. Now, the real world contains unstructured data like social networks, financial networks, molecules, proteins, etc. So, how we can represent these entities as graph, and how can we make the computer understand these structures? There are many ways to represent a graph. We can use node features, edge features, etc. to represent a graph so that a computer can understand it. The most common way of representing a graph is representing it as an adjacency matrix. By looking into an adjacency matrix, we can tell whether two nodes in a graph are connected or not. And there are different types of graphs. We can classify the graphs as directed graphs and undirected graphs. This classification is based on the direction of edges. If the edges are directed, it means the graph is a directed graph and the information flows in a particular direction. Here you can see we have a directed graph, and this graph has three nodes. So the information flows from node 1 to node 2, 2 to 3, and 3 to 1. There is no information flowing from node 2 to 1 or node 1 to node 3. Whereas in an undirected graph, information flows from node 1 to node 2 and back from node 2 to node 1, 1 to 3, and 3 to 1. So this is one classification of graph as directed graph and undirected graph. Another classification is we can classify the graph based on its weights. We can classify it as a weighted graph where different edges have different weights, which means the edge with a higher weight is having higher importance in the graph. And in an unweighted graph, all the edges will be having equal weights or equal importance. As I said, we can represent a graph by representing it as its adjacency matrix. And by looking into an adjacency matrix, we can tell whether two nodes in a graph are connected or not. In here we have a directed graph. So the dimension of the adjacency matrix will be V by V, where V is the number of vertices in the graph. And if the adjacency matrix if we write 1 for the edge weight in the adjacency matrix, then it means there is an edge from uh, that node to the other node. So in this graph, we have an edge from node 1 to 2. So from 1 to 2, we have 1. As this is this is an unweighted graph, we have 1 here. All the edges are having equal importance. And by looking into the adjacency matrix, we can tell which nodes in the graph are connected and which are not connected. So we can use this adjacency matrix representation for smaller graphs. When it comes to larger graphs like a large social network or a large e-commerce graph, then we cannot represent the graph as an adjacency matrix. Then we will use other representations of the graph. Like we can also represent the graph as node features, edge features, or the graph features, or there are different representations, or even we can sample the subgraphs in a huge graph and we can represent it. So this is one representation of the graph, which is adjacency matrix. Now, graphs are everywhere. We have social networks, we have knowledge graphs, we have financial networks, etc. So the companies like LinkedIn, Facebook, or Instagram, they use graph neural networks to analyze social relationship interactions and they recommend content. Companies like Google and Microsoft use knowledge graphs to organize and connect structured data. Companies like Amazon, Netflix, or YouTube, they model user item interactions and make personalized recommendations. Now, the power of graph neural networks become clear when we see different kinds of prediction tasks that we can solve with graph neural networks. There are mainly three categories of graph neural network tasks. First one is the node level task. Here, we try to predict something about an individual node. When we have edge level task, like link prediction, the prediction is about relationship between the nodes. And we have graph level task, where we predict the property of the entire graph. In drug discovery, it is an example of a graph level task. We can tell whether this entire drug molecule is toxic or safe. That is an example of a graph level task. Now let us understand different graph neural network tasks with examples. An example for a node classification task is in a social network we can have different classes of people. So in this network we have smokers and non-smokers. We have labeled nodes here. So these two nodes are labeled as non-smokers and these two nodes are labeled as smokers. And we have another node. We don't know whether this is a smoker or a non-smoker. So if the label of a node is unknown, we can predict the label of that node by using a graph neural network. And here we are classifying that node as a smoker or a non-smoker. So this is an example of a node classification task. So where can we have other applications of node classification task? In medicine, if we classify whether a cell is cancerous cell or a non-cancerous cell, it is another example of node classification task. In a network, if we have an academic network of students, if we can predict whether this student will pass the exam or fail the exam, that is another node classification task. Now, edge prediction task is an example of edge level task. So if we have if we have an e-commerce platform with users and items, there are edges between few users and few items. And here we don't have an edge. So if we can predict whether here if we can predict the probability of formation of an edge here, we can say whether this user and this item will interact. So if the user click on the product, then we can recommend advertisements and we can recommend that product to that particular user. So this is an example of an edge level task. Similarly, in chemistry, if we have the graph of a molecule, if we can tell whether two atoms in that graph form a bond, it can be another example of the edge prediction task. This is the exact task used by LinkedIn's link stage and Facebook's people you may know feature. So if we can predict the probability of formation of an edge between two nodes, we can recommend content, we can recommend advertisements, and we can tempt the users to buy those products. In a graph level task, we predict a property of the entire graph. In drug discovery, as I said, if we have a molecule, then if we can say whether that molecule is toxic or safe, that is an example of a graph level task. We are dealing with the whole graph. In biology, if we have different families of different graphs of proteins, if we can classify that graph into different families and say which family that protein belongs to, then it can be another example of a graph level task. Similarly, in finance, we can predict whether the transaction network is genuine or fraudulent. That is another example of a graph level task. Now let us see some of the applications of graph neural network, where they are used and how they are used. One of the most famous achievements of GNNs in science is the discovery of the antibiotic halicin. So this antibiotic halicin was discovered by researchers at MIT, and they represented the molecule as graph, and they used explainable AI and graph neural network to work with thousands of antibacterial molecules, and then they built a model that was able to solve the problem of antibiotic resistance. The molecule halicin came out as highly successful one. So this antibiotic was able to kill the bacteria that was resistant to almost all known classes of antibiotics. And this was achieved by representing the molecules as graphs and using graph neural networks and explainable AI to train. So how halicin worked? In chemistry, molecules are naturally graphs. We have the atoms and we have the bonds that connect the atoms, right? So In a graph, we can consider the nodes as the atoms and edges as the bonds between them. So each atom can have features like atomic number, charge valency, etc. And each bond can have features like bond order, length, type, etc. For decades, chemists used handcrafted molecular descriptors. They could not capture the true structure of the molecule. And when they started using graphs to represent the molecule, it changed the whole story. And using message passing neural networks or MPNNs, every atom start with a feature vector. And this feature vector is passed to its neighboring atoms through bonds. So if two molecules in a molecule is connected, then with the neighbors, these feature vectors can be shared. And after in each layer, this sharing happens. And after multiple layers, each atoms know about the entire molecular environment. And then we have a final pooling layer that calculates the graph level property of the molecule. So this what can be the uses here? This will allow us to predict the solubility, toxicity, energy levels, binding targets, etc. So instead of representing the amino acids or the molecules as just texts, if we represent them as graphs, then we can understand the patterns of the whole chemical environment instead of that single sequence. And this is how Halicin was developed by using graph neural network and explainable AI. And Chemprop was the core of the Halicin's model. So this works, Halicin works by killing the bacteria that was resistant to almost all classes of antibiotics. And this was a moment when we discovered AI and especially GNNs and graphs can be used to discover medicines and solve the problems problems like antibiotic resistance, which humans never thought of. Now, Google started with a graph algorithm. Will you believe me if I say this? Actually, Google started with a graph algorithm. The founders created PageRank, which treated the internet as a single graph. And each website was the node of this graph, and each hyperlink was an edge. If if there are many websites, and if there are many website links to a page, then we can rank those pages and say, okay, that page is more important. And if important websites link to a page, that page becomes more important. This was the first use of graphs in a large scale AI in a company like Google. And even today, modern Google search combines PageRank algorithm with graph neural networks and transformers. So Google was built on graphs. The knowledge graph and PageRanks are just natural evolutions of the same idea, and that is why Google invests heavily in GNNs even today. So Google search uses graph neural networks to improve information retrieval, ranking, and recommendations. Google's knowledge graphs represent entities as nodes and their relationships as edges in the graph. Now let us talk about YouTube's network. When we watch one video about graph neural network in YouTube, then YouTube immediately recommends us other content like other graph neural network videos, AI research talks, or Python tutorials for GNNs, and sometimes completely unrelated content like music. But it will be still relevant to you, right? So, how YouTube is able to recommend the exact relevant content or exact content which we will be thinking in our mind? How YouTube is doing this? To learn from this graph or to learn from the YouTube's network, YouTube uses a model, graph neural network model called Graph Sage, and this Graph Sage helps in recommending personalized content to the users. So it learns the user and video embeddings by aggregating features from the neighboring nodes, and these features can be information of users who watch the similar videos. GraphSage works by sampling a user's neighbors with other users and watch videos. So an example is if I am interested in graph neural network, I will be watching contents related to graph neural networks. I will also be watching other contents like AI research talks, and they will be talking about the relevant AI models. So YouTube automatically recommends me the content of my watch contents based on my watch history, my watch videos, and what people of similar interests or what my neighboring nodes in the graph are watching. So I may click on those videos as well, so they can increase their views and their interactions. So YouTube is using GraphSage for recommending personalized content, and GraphSage is a very popular graph neural network. They are using other algorithms and other graph neural networks also, but GraphSage is one of them. Now, let us understand Google's knowledge graph. When we search for something on Google, for example, say if I search Albert Einstein or if I search India's GDP, then Google doesn't just search for matching words. it searches for real world entities. It knows that Einstein is a person, India is a country, or if I search for graph neural networks, it is a machine learning model. So, how is Google knowing this? It is through knowledge graph. A knowledge graph is a giant network, and it has objects, events, and situations. The objects can be anything like a cat or an apple or a laptop. The events can be a sports event or the competitions or Olympics. The situations can be a pandemic or a disaster or a new event that everyone is interested. So anything can be the situations, anything like this can be the objects and the events. So these three components, nodes, edges, labels, schemas, identities, and context. This is how knowledge graphs work. Google's knowledge graph is represented through Google's search engine result pages, and we have different types of different nodes, edges, and labels in this huge graph. And these contribute to the uh, contribute to the what we can say. This contribute to the data sets from various sources, from various pages, or from various sources. It can be from anything, and these nodes can be the real entities. Like it can be anything like people, places, movies, books, or proteins. It can be anything. And the edges can be the relationships. Like if I have a question, like where was Einstein born? Then it can be a question and it can be an edge with relationships. It can tell Einstein born in Germany or apple is a fruit or this apple is a brand. It can give me those informations, analyzing the context. So a Google's knowledge graphs work by constructing a comprehensive view of the entities like nodes, edges, and labels, and each node has its own properties. Like if I search for a person, it has the properties like birth date or Wikipedia links or the professions or anything that is available in any page in Google. And if I'm searching for some chemicals, it can give me the chemical formula, the properties like atomic weight, etc. So instead of treating this as a text or question as a text, Google searches the graphs of connected meanings. An example for this is if I search apple, then it figures out whether you mean is the apple fruit or the apple brand. So it is by using the graph connections and GNN based rankings. And graph neural networks here help Google to determine which entity the user actually wants, whether that is the apple fruit or the apple brand. It ranks the information from the knowledge graph and recommend related searches. Like if I search Einstein, then it will recommend me related searches like Einstein's Nobel Prize or relativity theory, etc. So this can be used for powerful features like Google Assistants or Maps or YouTube. Now coming to AlphaFold, in 2024, Nobel Prize in Chemistry was awarded to AlphaFold, right, for protein folding. So here the researchers were recognized for using AI by modeling the amino acid sequences as graph and using Evo former in AlphaFold for predicting the protein folding. So it was using graph neural networks by modeling the amino acid sequences as graphs and using GNNs and transformers to solve the protein folding. This was very important and very historic for two reasons, as it was the first time AI and deep learning contributed directly to a Nobel Prize, and it proved that GNNs are not just tools for social networks or recommendation systems. They can solve deep scientific problems that humans struggle for decades. So let us understand more about this. Proteins are the basic machinery of life, right? They control the metabolism, repair, they transport oxygens, form form antibodies, regulate hormones, and everything in life, right? So every protein starts as a linear chain of amino acid, but to function properly, it must fold into a precise 3D shape. The protein's function entirely depends on this folded shape, not just the sequence. So if we have two proteins with similar sequences, it can fold differently, completely differently. And one small mistake in this folding can lead to diseases like Alzheimer's or Parkinson's or even cystic fibrosis. So predicting how a protein will fold just from the amino acid sequence is called as protein folding. And this was considered to be the biggest unsolved problems in biology for almost 5 decades. And why was it hard? So this was a 50-year-old grand challenge in biology, and it took it took almost 50 years to solve this. So the experiment will take years to determine whether a single protein structure, and a protein with 200 or more amino acids can take more possible shapes than atoms in the whole universe. So, determining the protein structure by traditional methods will take years or it is even impossible. But inside the human body, naturally, the proteins fold within milliseconds on their own. So, that means nature knows something that we didn't know, right? And that is why, for almost 5 decades, scientists believed we need physics simulations or something extraordinary to solve this. But in reality, by treating amino acid sequences as graphs instead of text, solve this problem. So it was by the help of data, which scientists worked for many years, and the data was made, and it is available in Protein Data Bank, and it was with the hard work of many scientists over years. The structures of proteins were determined, and we have them in the Protein Data Bank, and it is the work of many scientists over decades, and it was a starting point to train AlphaFold. So AI development set very clear benchmarks here. The evoformer was the core building block of AlphaFold structure, and it was by using graph neural networks by representing amino acid sequences as graphs and combination of GNNs and transformers. The researchers were able to develop evoformer, which is the main building block of AlphaFold's structure, and this was used to model the residue-residue interaction. And AlphaFold models proteins as graphs, where nodes are amino acid sequences and edges are the relationship between the residues. It can be the sequence neighbors plus the spatial neighbors. It can be like that. So each node stores features from the amino acid type and the evolutionary information. And AlphaFold models a protein as a graph where the neighboring residues exchange information through GNN based message passing. So GNN style message passing helps residues talk to the neighbors, refining their positional understanding. The evoformer block uses attention transformers to find long range residue interaction. It uses message passing to update the node and edge embeddings. And this is repeated for multiple layers so that each amino acid gradually learns its position in 3D. And finally, the 3D structure molecule can be predicted. And this is why AlphaFold worked, because proteins are not treated like sequences of text. Instead, they are treated as graphs in 3D space. And a graph neural network could naturally capture the patterns from the protein. And what in nature, in the animal bodies, what naturally happened with milliseconds, it was researchers were able to do that by using graph-based representation of amino acids. In AlphaFold, each amino acid can be treated as a node, and the model creates a graph where nodes communicate through message passing, just like in graph neural network. So to understand which amino acids are physically close in the 3D space, we can use this. And graph neural networks allow this message passing between the residues, ensuring the 3D structure is consistent there. And AlphaFold was using transformers uh, to capture the long range dependencies and improving the structure prediction. And this was made possible to predict the protein folding, which was a problem which researchers failed. Researchers were working on it, but we were not able to solve that great challenge for almost 50 years. And by representing the entities as graphs, we were able to solve it. Now let us see how LinkedIn matches the job seekers with recruiters using graph neural networks. LinkedIn is not just a social media platform, right? It is the world's largest professional knowledge graph. Every person, skill, company, it can be considered as the nodes of the graph, and there are different edges also. So this is a huge graph with billions of nodes and edges. Members are connected to their attributes like skills, titles, and positions. So every person's skill, company, job title, and recruiter is a node here. And the relationship between them, like the past employment or the skill endorsements or the job applications or recruiter message, all these can be considered as the edges. So the graph here mainly has 6 types of nodes. So even though this is a very huge, gigantic graph, it has mainly 6 types of nodes here. So the member nodes, the skill members are nodes in this graph. Skills are nodes, titles, companies, positions. All these are different types of nodes. To make job recommendations, LinkedIn uses the graph neural network model called LinkSage. LinkSage is LinkedIn's flagship graph neural network developed by LinkedIn's researchers. So this is an adaptation of GraphSage, and this graph neural network handles this huge dynamic graph with billions of nodes and trillions of connections. Let us see how that graph is constructed. So the nodes include all these 6 types, and edges can what can the edges be in this graph? The edges can be if a person worked at a company that can be one edge. And if a person has a skill, that skill between the person and the member can be considered as an edge. So here member 2 is having skill 1 and skill 2. Member 3 is having skill 2. So all these can be considered as the edges. And if a recruiter posts a job, it can be considered as that job can be considered as a node, and that posting can be considered as an edge. And if a recruiter views a candidate's profile, that viewing can be considered as an edge. Messaging in LinkedIn can be considered as another edge. So all these are different interactions in the graph and different nodes in the graph. So this is a huge dynamic graph with billions of nodes and trillions of edges. Now we can have two types of edges in this LinkedIn's graph. First one is the static edges. The edges can be static when the member is connected to their listed job title. That can be considered as a static edge. And edges can be static, like if we have some educational details that does not change, right? So it can be considered as a static edge. Whereas we have dynamic edges like browsing history, or if I apply to a job, I can apply to multiple jobs. So, and I can also post multiple jobs. So this can be considered as dynamic edges. And these dynamic edges evolve based on the relationship derived from the user interactions. And Linksage learns by aggregating the features from the neighboring nodes. And if a user has some experience, like if a user has experience in Python and machine learning, then the model automatically searches for job nodes where these skill nodes overlap. And similarly, it recommends candidates to the recruiters based on these skill nodes and the job requirements. So instead of treating that job requirements as text, it is treated as entities in a graph, and it is matched with the candidates and the job postings. Candidates are recommended to the recruiters and jobs are recommended to the job seekers. So when a user applies for a job, an edge is formed between the job seeker and the recruiter. Instead of treating all the skills equally, Linksage has a scoring model to identify the relevance. Traditional machine learning models fail here because the data is not in rows and columns. It is a huge network of data. So this data was relational, and GNNs allowed LinkedIn to treat everything like a network and match people to opportunities based on the context. So instead of treating this as if we have a job posting, instead of treating the requirements in the job posting as text, it was considered as the nodes and edges in a graph, and the recommendations was made. Now let us understand about Twitter's temporal graph network. Twitter is dynamic and real-time social network platform with billions of users and tweets. Here we can see an example graph. So when I say dynamic graph, it means the graph changes every second. So we can have different users in this platform. So if someone likes a tweet, or if someone follows another user, or if we reply to a tweet or retweet, all these can be considered as timestamped interactions. So if we have different timestamps like 1, 2, 3, in every timestamp or in every second of time, there can be new events happening in the network. Here the time matters. The graph is dynamic and the time matters. This is why Twitter uses a temporal graph network, which is a type of graph neural network that handles event-based streaming data. And this temporal graph network can handle dynamic data that changes with time. The frequency is very, very high. Temporal graph network work in 5 logical steps. It has 5 modules: the memory module, message passing, message aggregator, memory updater, and the embedding module. Let us understand how each of them works. First, here you can see the information is processed in batches. We have different batches, and first we have the messages here at every timestamp. There are 2 timestamps, T1 and T2, and we have 4 messages here, M1, M2, M4, and M3. And here we have the memory module. So memory module is this memory module stores the history of all the interactions happening in this graph. So each user or node has uh, a history of events, like a user can follow another user in a particular timestamp. So that can be considered as one event. And a user can enter the platform, a user can exit the platform. All these can be considered as different events in the graph. So this memory module stores the entire history of the nodes and the edges. So at this particular timestamp, this user interacted with this item. Item can be the tweet or a post. So the memory module stores all this information. Then we have the module message function. So whenever whenever an event happens, like the event can be liking, following, or retweeting, a message is created. So this is what the message function does. Next, we have the message aggregator. So when the events are happening, what basically happens is the information is shared with the neighbors of a node, right? So the message aggregator aggregates these message functions and updates the features. The memory updater module updates the user's memory, and user's memory can be like it. Here we had the messages M1, M2, M3, M4, M1, M2, M3, M4 at different timestamps T1 and T2, and after collecting the messages, passing the messages, and aggregating the messages, the memory is being updated in the dynamic graph. The updated memories are the S1, S2, S3, and S4 at two different timestamps. And then the node embeddings are generated. Here we can see at every timestamp for every nodes, we have the different node embeddings, and these node embeddings are updated. And then the edge probabilities are calculated. So at the starting of the webinar, we said we can have different types of tasks in a graph neural network, like node level task or edge level task. So this is the example of an edge level task. If I can predict the probability of formation of an edge between two nodes in this graph, then I can recommend content according to that. So I can recommend the relevant advertisements. If this is instead of Twitter, if this is an e-commerce platform, then I can recommend advertisements of products that that user might purchase. So here basically they are calculating the edge probabilities based on the updated memory and calculated node embeddings, and they are able to tell whether an edge, whether there is possibility of formation of an edge between nodes 1 and 2 at time t1, or nodes 3 and 4 at time t1. So this allows Twitter to predict who you are likely to follow next, or which tweet should appear on the top of your feed, or which tweet might go viral soon, or it will also help to detect the fake accounts or coordinated misinformation. And temporal graph network help Twitter to reduce timeline delays and improve the relevance in tweet ranking. So this can be extended to predict the user item interaction in an e-commerce platform. It can be used for deep learning on dynamic graphs, where everything is represented as sequences of timed events, and combination of memory modules and graph-based operators can be used for this. And I have personally worked with temporal graph networks for e-commerce data, and I have found out that TGNs can outperform previous approaches by being more computationally efficient and working with dynamic graphs. So this is a research area that we can where we can apply temporal graph networks and have different types of research opportunities, different research problems. And this is exactly what we are doing at Togo AI Labs. We have research collaboration programs, we have research mentorship programs, and if you are someone who wish to transition to AI, we provide AI transition mentorship also. So if you are I'm collaborating with people on different graph neural network research projects. So if you are interested in working with us on graph neural network research collaboration, you can visit our website, uh, togolabs.ai. And if you visit our website, you can see our different programs. Like there are self-paced courses available where we have the recorded lecture videos explaining graph neural networks, how they work, mechanisms of graph neural network, covering everything from basics. And if you are interested in collaborating with us on GNN research, then you can visit our website, togolabs.ai, and you can enroll in the GNN research collaboration program. So I hope this session was very useful for you. So I thought we will be able to wind the session a bit earlier so that we can have a question and answer session also. But I think it is already the time. So if you have any questions or if you want to interact with me, just send an email at aishwarya@togalabs.ai, so we can have interaction. And if you're interested in discussing your AI or GNN research projects with me, or if you need any guidance or mentorship for conducting your GNN research, feel free to reach out to us. So you can email us. Once again, let me thank everyone who joined the session, who got time to join the session. I know everyone is busy, but thank you so much for joining the session today, and looking forward to working with you on amazing GNN research projects. Do visit our website, togolabs.ai, and explore our programs. I'm sure you will enjoy our programs. We have self-paced courses as well as research programs. So thank you so much. And okay, thank you so much for joining.